Another type of energy is thermal energy. Anything that has a temperature above 0 Kelvin possesses thermal energy. This corresponds to the random motion of the atoms that make up the object. The higher the temperature, the greater the thermal energy, and vice versa. This energy comes from the kinetic energy of the moving atoms, and in solid from the chemical potential energy in the bonds that hold its shape. As things get hotter, they have more kinetic energy bouncing around, which means on average they're further apart, which means they've stretched those bonds. Right. Imagine dragging a box a distance delta x along a table while it suffers a frictional force F sub k. That force does work equal to Fk delta x, which adds energy to the box table system. But the box isn't going any faster, and it isn't getting any higher. So the change in kinetic energy and change in potential energy are both 0. Where does that energy go? It goes into heating the box and the table. And it's important to understand it's the interaction, and so both of them get that. And so we can say that the amount of thermal energy gained is F sub k times delta x. Over here we have a picture, a thermal image of a box being dragged along a floor, and we can see that it's left behind a trail of heat, and you maybe can see that there's a little bit of heat here, although obviously it's a little hard to tell if that's the bottom. Are we seeing the bottom of the box, or are we seeing the sides of the box where it's being held? You can probably see the person's fingers right there holding it. Here's a video that shows that whole thing go on. With your eyes, you can't see the heat. So this is sort of uninteresting, again. And you can't really see anything different. But with the camera sensitive to the infrared, we can see the radiation it gives off. We see both the trail and how much the base has been heated, and the person. Your book has a not particularly great model of what's happening. It's not bad for visualization. We know that ultimately this is not how friction works, and therefore this is not really exactly what's going on, but it's pretty close. The atoms at the interface pull on each other as the box slides along. All right, they've bonded very weakly, and so anytime they're in contact, they've bonded very weakly. This is actually not a bad model for how friction works. As you pull on it, you distort the bonds and store extra energy in them. Your book calls it elastic. I'll call it elastic-like. It's chemical potential energy, really. It's not like a spring for sure, but it's pretty close. Behaves mathematically about the same. Eventually, you'll break those bonds, and that elastic potential energy becomes kinetic energy as the atoms snap back to where they were before, and then that expresses itself as heat as they share that with other atoms around them. Why do we say that this energy is lost as heat? Because it's very hard to reorganize it back into useful work. We did work on moving the box, but if you have a thing that's just hot and you put the block on the table, it's not going to suddenly slide across the table. The energy in thermal energy is disorganized. It's not easy to use. It's distributed over the entire subatomic and atomic scales, and so therefore calling it waste is maybe a little pejorative, but it's hard to take use of. All right, blocks with initial kinetic energy of 4 joules comes to rest after sliding 1 meter. How far would it slide if it had had 8 joules of kinetic energy? Well, this problem, we want to think about that delta K is equal to delta E therm, which is the force of friction times delta X. This doesn't change. So if we've doubled K, then we've doubled delta X, and we should get 2 meters. A block with mass 12 kilograms is moved across a table back and forth 30 times leftward and 30 times rightward, each sliding 25 centimeters each time. The coefficient of kinetic friction between the block and the table is 0.2. How much thermal energy is added to the block table system in joules? Well, we draw a free body diagram, which is pretty easy. We have the object, there's a weight pulling it down and a normal force keeping it on the table, and then there's a frictional force resisting. and then it moves this way in 0.25 meters. We're going to do one trip at a time. So on one trip, it moves over 0.25 meters. And so the energy it gets in one trip is the frictional force times delta x. But frictional force is mu kinetic times the normal force. And the normal force is clearly the weight because they're in balance. So we end up that the frictional force is mu k times m times g. And then we multiply by delta x to figure out the thermal, and we get something like 5.88 joules. But there are actually 60 trips because they said we go, this is one trip, and we go 1, 2, 3, 4, 5, 6, 7, 8, etc. until we've done it 30 times back and forth, which is 60 times total. So we get 60 times that number, which is 352 apparently.